they are looking for positions in Hyderabad, GIAN. There is an office in Hyderabad. I know Baru in Hyderabad. I don't know GIAN. Not that far from there.
Had a full house, but it's a little over 10 o'clock. We gave that grace period of 2 minutes, so 10:02. So I thought I would start, otherwise, we get delayed in the lunchtime. Yeah. So first thing I wanted to ask you was, I know we are slightly ahead. So anybody has any questions on this? So lectures 3 and 4, we are supposed to cover 4 today, but I think we were already ahead. So I wanted to ask you before I move on to the next lecture. So, any questions on this? So if you remember, I just want to spend maybe a few minutes trying to recap. There are so many different topics we were looking at. One was, if you remember, optimality, right? And we talked about finite horizon and infinite time horizon. So we want to look at it, and then we also talked about Q-learning as part of the machine learning side of it for linear systems, because we are going to repeat that every chapter when we bring some other things. And we also talked about neural networks if it is for nonlinear systems, right? And then we also talked about the issue of network control systems. What happens when you don't have a network and you do have a network? So you guys need to realize that that's very clearly, it has to be in your mind. Okay? So I want to just pause here and ask for, if you understand that, it's going to get more difficult. And did you guys, I don't know whether Dr. Vera gave you the code. I was planning if he comes here, I wanted to ask him to share the code. He shared already. So I suggest that, okay, since he's not here, maybe I'll say this. I suggest that if you have a laptop and you have access to MATLAB, this is a good way. I know tutorials is in the afternoon. I would suggest that you start running the code, and you have the slides as well, right? And I think you may want to kind of look at it how the code was written. Of course, remember, there's not many comments because this is not a commercial code that we develop, right, as a university. Is like you, if you're doing a research, you write a code that works, but you really never spend time on commenting and make it commercial. So that was not the goal, right? And the goal is for you to look at these code and see how it's, when you cover some slides, see how those equations are coming in and have you play with it. And when you're trying to play with it, I suggest you save the original one and then you rename the file, and then that way if you make changes to it, you don't get stuck, you always can go back. Alright? So I encourage you to do that so that when you come to the tutorials, of course, not everything I can answer. Usually I don't get involved in the MATLAB program. And so only thing is you want to see whether you get similar results And second, how many of you have access to that book that which is what I listed here? Okay, so there's only one. I suggest that each of you should have an access. Share, Sarah shared. So what is the PDF? Yeah. So, but I don't see anybody raising their hand now. Okay. Right. Now there is a difference, right? In the slides, I don't put all that information. That's why I asked you. But if it is, and if you read the book, there are a lot more stuff in there. That's why I think it is better. So you will see there are things that were there, not on the slides, and sometimes that would help you. And why I suggested is because sometimes when you are looking at the MATLAB code, you remember I didn't go through in details all the math equations, but I think what I wanted to do is the next few minutes, I wanted to cover the Q-learning one more time. And I think Q-learning for linear and the other one non-linear. Every part of the slides have that. And why I'm doing that? Because there are so many different things, many of you may not have the background. And now, just like she said, that's where the jobs are. If you remember, I keep saying that machine learning and all, that's where it is for control. And not for control, pretty much everybody. Okay? So the traditional control stuff and all is gone now. You need to have that background, but very little that you will find because these new stuff essentially have the benefits. That's why you've been attending and you saw that what's going on right now. Right? So it's important that you should have that background, the traditional one, but that goes without saying. But you also need to have what's happened, and whatever I'm covering is over 10 years old, more than 10 years old. The book has come out in 2016. Okay, that's about close to 10 years. But the work has been done 5-6 years prior to that. You see? So, and so that's how it takes. And industry takes a while for that to come out. So there's a lot of data that I skipped, but you will see that we talked about a little bit, and I'll show you how we are using the data and all that inside. So this is a way to do data analytics as well. That's what the controller is doing, implicitly. Okay? So, and I think since we didn't have time, at least I didn't know, so we kind of went fast. But remember, that's why I said look at the book, because we are not going through equation by equation. The book probably explains a little better. And it cites some papers of us. You may want to grab the papers if you don't have the understanding, and the papers might give you a little more detail. You see? Okay? So that's what I wanted to tell you, because you remember we talked about Q-learning, we talked about neural network, but then we also talked about deterministic systems. Then we said, okay, whenever we have the network in there, it becomes stochastic. And we skipped all the basics of like how you apply those expectations and all, right? And remember I asked you the Monte Carlo. Today also we'll see, it's mostly averaging aspects. You run the same program multiple times. Every time you run it, it will pick up a different set of initial conditions, and you average those results out. That's how we do in stochastic. And this is typically done in the industry. You see, we normally don't run one time and just stop it. So these are the things that you've got to keep in mind. Not everything we kind of cover here, okay? All right, so any questions now? Let me ask you. He does assume that or no?
Not assume, but I understand.
Right. I think, you remember, we talked this about it. So the time delay, essentially we assume it's bounded by a d bar. And if you look at the model, to incorporate those delays, there's an expansion that goes there in the B's, right? That expansion goes all the way to u of k minus d bar. That d bar is the delay, right? So you could go more than one sampling interval, but as you know that there is a problem, as I mentioned, when there is a delay, that means that the system is an open loop. Okay? But there is the control called event triggered control. There the delays can be more than a sampling interval. So it is possible to have a delay more than a sampling interval. Okay? So now there are some additional things you got to remember if you have that kind of a situation. The open loop system has to be stable within that time when the system is running open loop. Remember that. You see? Because if the open loop system becomes unstable, there's nothing you can do. Okay? So I don't know how many of you have taken a course on nonlinear control. Okay, so I'll ask you this because that relates directly what she's saying. Okay, did you guys study what we call finite escape time? Have you heard of that, what it means? So finite escape time is if a nonlinear system, if you apply even a bounded input, for example, the system states can go to infinity in a finite time. Okay? So many times when we deal with nonlinear systems, we assume that the system doesn't have that property. You see? And why is this related to this, relevant to this discussion? Because if a system has that property, then if the system is running open loop, right? And in the network control system, what happens is there's a whole signal. So since the packets get dropped, what they do is just like in the digital control, they maintain the previous value of the control input rather than making the control input equal to 0. There are two ways you can do. One is the control input. Until you wait for the next one, you can make it 0, or you hold the same control input that you have before. Okay, so that's a bounded control input. So if you are applying a bounded control input and if your system has a finite escape time, and you assume that the d bar, the delay is more than a sampling interval, the system is running open loop. And it's possible that the states already go to infinity. You see? So in most cases, we assume that the system doesn't have a finite escape time, or in other words, if you look at, there's another book that we wrote on event triggered control. Okay, we were the first ones actually looking at it after the paper was published in event triggered control in 2009. Okay, we were doing in the adaptive side of it. So one of the things they assume is the system is input to state stable. And that assumption is very critical. What it says is during that, the traditional nonlinear guys don't prove what happens within that event triggered interval. So what is event triggered? I don't know how many of you know. Remember I mentioned there the goal was to stretch the sampling interval. It becomes aperiodic. Remember the sampling interval traditionally is periodic. But I already told you when you have a network control system, when you are exchanging the state information as well as the control inputs, the network bandwidth is limited, so it can get congested, right? And therefore, you really want the interval to be stretched, the sampling interval. And by doing that, you are not really transmitting at every sampling interval, right? And so, but then you have these issues like what she said. Okay? So, in the event triggered control, basically you stretch that sampling interval and it's aperiodic. And you only sample when you need it. And when do you need it? When the system is about to become unstable. So, the traditional nonlinear control guys, where they assume the dynamics are known, they basically say that the system is input to state stable. So the same idea, input to state stable means when you are applying that, in that case, when you are applying the input, the system state has to be stable when the system is not closed loop. You see? So those assumptions you have to have it. Okay? So we relaxed it because If you look at my work on event triggered control, I have two cases in the Lyapunov proof. One is at the sampling interval and within the sampling interval. So the assumption that, coming back to your question, that the D bar less than a sampling interval is not needed, but it's needed in some cases because of that issue. You are running the system open loop and you want to make sure the system is stable. You see what I'm saying? So if the open loop system is not input to state stable, or if it has a finite escape time, then you can't do anything. This is the property of the physical system, nothing to do with the control. Okay? Any other questions?
Sir, your implementation of the control requires that expected values of these all are expected.
The history, yeah, that's right. That's what I was about to say. Yeah, that's right.
So when you are implementing that one, you are keeping all the previous.
That is in the memory. That is exactly the data science people are right now doing. Data analytics. Yeah. So there is some history, and I'm going to go over quickly since we are already ahead. And then, so there is some history when we were showing that Bellman error convergence. And so I built a system by using the history of those errors, the temporal difference errors. So I do keep some in the memory. That is correct. Yeah, memory. And the same thing, remember, we also have an augmented state vector. The same thing, right? Yeah, so in the augmented state vector, you are keeping the previous inputs, the z of k. So not only the current values, but you can. But how many you keep it is up to you, based on the system.
There should be some limit will come.
That is correct. The memory and all that. That is correct. And it also varies with the system. Not every system you may need a significant number of previous values. That is correct.
So is there any regression?
I think we have not actually. Yeah, we never really spent time there. We try to pick because usually the students they rush to finish it off always, right? So we never really gone into like how many you have. But I think probably it's very difficult to come up with a relationship. So the only thing you have to do is mostly trial and error. Yeah.
That's one thing. Second thing, sir, you are talking about that suboptimal.
Yeah.
So you are doing that one and you are fixing it here.
Right. That is correct.
But sir, I don't remember, sir, but in that procedure, there should come something like covariance or something should come. But matrix covariance should appear when I explain it that. Because in that time you are giving
Right. So no, there is covariance. That is initial value of P naught. There is a covariance matrix which was, because you remember you need to have an initial value to start with. That is basically, those are the, I didn't even talk about that, but that's where you need to have that. Right. No, it is there. So the initial value would become like in a stochastic Kalman filter, you have the covariance and all. Yeah. And the reason we don't talk about it becomes part of the system, whereas in a traditional stochastic optimal control, they bring it out because of the noise that goes in. Because here I did not cover the part, the stochastic in my case from the system side, but not from the noise or the, remember I mentioned that you could have that too, then you will have to define the covariance of the noise and stuff. Oh yeah, sure. Yeah. I think those you can't skip. Any other questions? So, Professor was asking this a good question, how many past values you look at. So we haven't really spent time on, because we know that it varies with the system. Some systems which change fast, you may have to keep longer, and the ones that are slow, you may not need that many values, okay? But beyond that, because memory is cheap. Even the computations now are getting cheaper now, So, but you have to have some memory, okay? And I'll show you. I think those are good. So, any other questions before I can kind of point out where things are? So then we'll go into the new chapter. Any questions beyond these? So if you look at it again, we talked about it, right? If you have finite horizon, you have a terminal constraint, which is non-zero. If it is infinite horizon, the terminal constraint will become zero. We talked about that, okay? And either way, if it's a linear system, we get Riccati equation for finite time. And that's a time varying. The optimal gain is time varying. If it's infinite horizon, the Riccati equation for a linear system becomes what? Algebraic Riccati equation. They become constants, right? Remember that. It becomes algebraic. And the Kalman gain or the gain matrix becomes constant. Okay, don't forget that, okay? And if you take the same analogy into the nonlinear domain, the Riccati equation becomes HAB equation. So for infinite horizon, the HAB equation is not explicit function of time. Explicit function of time, remember that. Now if it is finite horizon, then you should have a time t, then you will have an extra time t. So when you do that, the value function that we talk about also will have an explicit function of time. So v is x of t comma t, because that's also varying with respect to time. Now the only reason we don't deal with this for tracking, I didn't talk about tracking, but the reason we don't deal with that is because in function approximation, when you're using neural networks for instance, you have a problem because you have to have it on a compact set. And so when time is infinity, it doesn't stay on the compact set. So when you have a time-dependent trajectory, typically a trajectory tracking problem is explicitly a function of time. And so there's a lot of discussion, even though simulations work, but mathematically it is not correct to have a tracking. Here is regulation, but you can do the same thing on tracking. And if you do that, then you have the time, and therefore neural network approximation mathematically is not correct, although it works pretty good. Whereas for finite horizon, the actual activation functions will be an explicit function of time. I'm going to show you that. Don't pay attention to that. And that's okay, because they're finite, since it's a finite time, n is finite. Okay? So it is okay to have that on a compact set. But for infinite horizon, this is a problem. So normally, so there's a way to do it. We take the augmented system approach. That's also similar to what I presented. Okay, so the solution to HAB equation, you see that for a finite horizon is time varying, and for infinite horizon it becomes a very standard, like algebraic Riccati equation. So here is again, I'm going to go back again, the LQR problem. The linear quadratic regulator problem, where you have this is a discrete time system. In this case, A and B are constant. It doesn't matter. A and B can be time varying. You get the same set of equations. So you see that we are defining an index. This term is called terminal constraint. You see that? And Sn is the terminal weighting matrix, which is up to the designer. You choose that. And here you see that the second term, I equal to k to n minus 1, this is what we call as, this term is called cost to go. The cost that goes within that n minus 1, 0 to n minus 1. And is always quadratic. You can pick non-quadratic functions. There are benefits to that. But for you guys right now, we are assuming this is quadratic, okay? So if it's quadratic, you see that there is a quadratic term in terms of state, and there is a quadratic term in terms of control input. Because you want to minimize the error in the state as well as the control input. That's what you normally try to do, right? So we talked about the derivations earlier. You end up in a Riccati equation because you have to solve for S of k. And that S of k goes in the control policy, and you see that kk is a function of S of k plus 1, A and B. So S of k plus 1 comes from the Riccati equation. Now, remember I said Riccati equation you solve backward in time. Now look at that, S of k is a function of S of k plus 1. So that's why you start with S of n. S of n is already given here. You see this? That is the terminal constraint. S of n is given, and then you come backwards. You normally solve backwards. S of n minus 1, S of n minus 2, and S of k, and then that's how you go backwards from the equation. and typically there's no closed form solution. So in Riccati you may find it under some conditions. So basically it's a challenge. Okay? So it's a quadratic equation and you can use numerical methods. But the problem here is it's a backward in time as we talked about it, and you need A and B, right? That's basically what that is. So if it's a nonlinear system, so here F and G are nonlinear, smooth, then the same idea. You see, you have a performance index, and the performance index has a terminal state constraint, and the terminal constraint is given by the psi, plus this R is the cost to go. And you see that we use a recursive Bellman equation, V star xk. You see this V star is explicit function of k. Now remember, this is what I was talking about. Why is it explicit function of k? Because this is a finite horizon. For finite horizon, the value function becomes explicit function of time. Just like the Kalman gain becomes a time variable. Okay? And so now what you do is you write this as the k to k plus 1 and then k plus 1 to n minus 1. So that's what that is. So then the optimal control policy is basically not only requires G dynamics but partial V star over partial x of k plus 1. Now typically V star is unknown. That's why we use a neural network. And that neural network is called what? What is that neural network that approximates the value function? Huh? That is called critique. Critique approximates the cost function. So there's another neural network we use to approximate the control input because you don't have the G. And that neural network is called what? Actor. Because it creates an action, generates an action, which is a control policy. Okay? So you cannot forget that. So this is a discrete, and here is the continuous. It's exactly analog to this. Okay? Instead of summation, you have an integral. Generally, a JB equation, even though it's not time varying, doesn't have a closed form solution. Even if you know the dynamics, F and G, it's still very difficult to solve it. And so, the idea was you want to use numerical methods to solve it. And that's what we call policy iteration or value iteration methods. So what they do, remember I said, you between any sampling interval, you hold the time, and then you are using the numerical methods to solve that JB equation. Okay? And again, that part is how many number of iterations you need is also not known. You see what I'm saying? So that's the problem that you need to remember that. And there are some references, I talked about it. So, but the goal was online and forward in time. I think that was the goal. Because otherwise we can implement backward in time optimal control in any of the applications. Okay, even if you know the system dynamics, even if you know that. So, this is the same thing that we talked in discrete time earlier I showed you. So, the Q-learning essentially relaxes that problem. That is, two things it relaxes. One is the backward in time, and what is the other thing it relaxes? A and B. A and B, that is correct. You don't require A and B. So you cannot forget that. This is with or without the network. Remember that. We do this and then we are applying the same idea. So it's no big deal. Once you understand this, trying to go there. Remember, that's why I'm going through. Because we're going to talk about the quantization at 11 o'clock. So I want you to understand this reinforcement learning stuff. And I'll also show you some history stuff. Okay? So the way it works is you define a j of k plus 1 is equal to this. So you remember that Bellman equation is a recursive equation. So you use this equation, this v star of x of k plus 1. So the v star of x of k plus 1 is basically the j star of k plus 1, which comes out here. See that? That is what that is. Okay? So it's very critical. In some slides I have the details. So you see this part is basically that. Okay? So this equation becomes x qx plus u or u, that is this, plus, so this x of k plus 1 transpose s of k plus 1 times x of k plus 1. So that's what that is. So now what is x of k plus 1? X of k plus 1 is what? Is equal to a times x of k plus b times u of k. From the system dynamics. Right? That's what we did here. You see that? X of k plus 1. Oh, I think it doesn't change here. Okay, so that's basically, so what you do is, wherever there is x of k plus 1 transpose, you put a times x of k plus b times u of k transpose times s of k plus 1 multiplied by a times x of k plus b times u of k. Okay, so now what happens is, you see that there are terms with x of k, u of k, u of k. So you combine that and then you write it in the form of xk, uk. You pull it out. So xk, uk. And then you have a matrix. This matrix is g of k. And then you have x of k, u of k. And that's how we got that matrix. You see? It's no big deal. It's not difficult at all. Any questions here? Because we keep using that if it's a linear system, linear network control systems and so forth. Any questions, guys? It's not that hard. Okay? So once you have it, now look at that. You really need this term. We don't need this whole matrix, but you need that term. Inverse of that, multiply by that. And if you have that, that's your nothing but your kk. That's nothing but your gain. Now by doing this, and you forming this into an optimal adaptive control problem, because you don't know this matrix. Do we know this matrix if A and B are unknown? No. Because you see that there is A, there is a B. So we don't know this matrix. So we use what we call is Kronecker product. And you pull that, you make the matrix into a vector, and you pull it out. And the rest x. So you write this as g bar, or in the book, we put g bar transpose times some phi of whatever, okay, x comma u. Because you see that there is a xk, uk. So you pull it out, and this basically is a long vector. So in consisting of that, and then you create it as an adaptive control problem, and you estimate g hat at every instant of time. Then you reconstruct that big G, and then you compute the k. That's what you're doing. It's simple as that. Okay? So you compute that, you estimate it, so then this becomes adaptive control problem. And then you estimate at every time this, you see that? And then you multiply by the state, and then you get the optimal control policy. Now remember this. For finite horizon, you also need to have the time, n minus k. N is the final time. K is the time, current time. So you're using the explicit time, and this is exactly what I said here. Okay? And that becomes an adaptive control problem. All right? Okay. So here is the inverse. Remember I said, here is the inverse times that. Okay? All right. So that's for linear systems. So that's called Q learning. So Q learning, you relax A and B, and it does work. Okay. So let's see here. Now, Professor asked me the history, right? I'm going to show you this. So here, now you see this history stuff. So what you do, you have this n minus k minus 1, and you get that in the basis function, and you get this. So now look at that, the Bellman error, this is what I want to show you, is given by this expression q hat at k plus 1. So this term is the difference in the time with the cost to go. So therefore the Bellman error is also called temporal difference error in reinforcement learning. So this is where you use adaptive dynamic programming. So that is where you are bringing in the adaptive dynamic programming, which is the reinforcement learning concepts into this. Okay? Now look at that. There is also a terminal constraint error because it's a finite horizon. Now look at the update law. This update law is basically try to solve it by minimizing the square of the Bellman error and the terminal constraint error. Okay? So now this is where the professor was asking. Look at that. You see this? That's the history. So I'm not formulating just this current value. I'm formulating that regression function as a history. Okay? And you need the history. The more values you have, the better is the convergence. We know that. But so you see that here, I went all the way to k minus 1 minus j, previous values. You see? Okay, so the same thing in the cost to go, also you are trying to go to the previous values, k minus 1 minus j. And the number of previous values, typically you are stored in the memory. The number of values is up to the designer, how many you need, and it may vary with the system and time constant. There are so many different things. Okay? So once you do that, here is the update law. The challenge is how to come up with the update law. So all this with respect to, see this term is the Bellman error, but history. That big E, that's basically history. And you can see here, EK total is the Bellman error and the terminal constraint error. And then this term essentially has the history. So keep this in mind. And you see, Professor, this is where you get the initial value. That's where you set the covariance, of that particular initial value of the system, whatever, right? So that's, and then here is your control input. The actual control input, you take the G and you take this term inverse and this is hat. Hat stands for estimated value. Got it? And the goal would be is to drive the hat to the actual value. That's what the adaptive control does. Got it? And the proof shows that it's basically driving towards that. So when we prove it, we show a whole lot of stuff. We show that, first we show that the xk converges to 0 or small, depending on what happens. And then g hat approaches g, and v hat approaches v, and u hat will approach u star, which is the optimum. That's a part of the proof. Any questions, guys, here? So this is the idea for linear and linear system, and so here are the proofs that normally we talk about. Okay, I didn't go through it, but you guys can go through it. And we talked about the output feedback as well last time. Okay, so now remember those update laws here, the adaptive observer, those are developed as part of the PhD work. And remember I said, and how do we derive those? Using Lyapunov. And those are, most of the students that work with me spend probably 9 months out of the 12 months doing that. And the 1 month in just getting the results. And 1 month is basically coming up with a solution. So most of the time we spent is on the proof. And that takes an enormous amount of time. Yeah. Now, is there any better way? No. So all people who are doing research, the main challenge is in the mathematical equations. That's why I told you simulations work, but we want to ensure that theoretically there is a guarantee. Yeah. Otherwise in control theory you can't publish a paper. Okay, any questions, guys? So now in the update laws, you see the update laws are driven by the Bellman error. See, this is the output error for the observer. This is the Bellman error. Look at that. So that's what the Bellman error is, the measured quantity. So we are using that to drive the update law. So basically it's used to tune, and you learn the G hat, and over time the G hat will be pushed to G. And when it gets pushed, the Bellman error keep going down to 0. Remember, that's what those parts are. Okay? So finite horizon, you have two errors, and we sum them up. The terminal constraint error and the actual Bellman error. Remember that. Whereas in the case of infinite horizon, you only have a Bellman error, you don't have a terminal constraint error. That's all it is for Q-learning. The same idea works when you use neural networks. Okay? Any questions here, guys? Any questions? So this is Q-learning without network, but when you have a network, it becomes A becomes AZK, B becomes BZK, and wherever you have those terms, you put the expected value. That's it. There's nothing different. The approach is identical. The expected value doesn't change anything. You only pick the covariance. Initial state, you pick some sort of a covariance or variance matrix because it's now getting into the stochastic domain. And you don't do it once in the simulation. Most of the time, you probably have to do 1,000 or 10,000 times. You repeat it, and then you average those values. So the states, errors, everything has to be averaged when you are plotting it. For ergodic behavior, that's called ergodic systems, ergodic behavior. Okay? So you guys heard of ergodic behavior? No? Oh, you guys might have heard. I'm positive. Undergraduate. So as a homework, check it. It's called ergodic behavior. E-R-G-O-D-I-C. I'm positive undergraduate. We all have one class, and it would come one of your math courses, and we all forget. Unfortunately. And what is the best way to remember, guys? Do you know? What's the best way to remember? What's the best way? Huh? Learn is okay. But what is the best way? You will never forget. Let's say a lot of things we do, right? Riding a bike or driving a car, whatever. Why we won't forget? Practice. So you implement, if you apply this, you will never forget. So that's the problem with the Indian system that I was talking. We do a lot of exams, and after the exams, next you have a different set of courses. We do all that, but whatever happens in that class, we never use it again, right? And that's the problem. That's why we forget. I'm positive Indian system is strong in terms of those kind of things, fundamentals. But we never go back and apply. That's the problem. And that's why we learn a lot, but we never apply, and therefore goes up. Okay? Any other questions? All right. Now, I know some of you are master students, right? Maybe I'll take a little time about masters and PhD here. This is very critical. Let me show you this. Okay? I know all of us need money. Yeah. All of us need money. So, a lot of us just go for masters, don't care about PhD. But I'll give you in US, and I'm positive it's the same thing here, because I have students who came here, they have faculty in IISc Bangalore and some IITs, okay? So let me tell you what happens. So you have a master's, let's say MTech, right? You have a BTech, and this is MTech. And MTech takes about 2 years, right? Approximately. Somebody told me MTech students are getting less paid than BTech. That's not true. Actually, there is something wrong. If you don't ask more, there is seriously something wrong. Okay? That's not true. Okay? Let me give you in US, because I know the numbers. So BTech students get anywhere right now between $80,000 to $85,000. All right? So an MTech student, the starting pay for MS, we call MS here, we take MTech. So usually varies from 85 to 100K right now. Okay? So PhD usually takes between 3 to 4 years. If you have an MTech, it's much faster. A PhD gets 150K. This is the minimum. Okay? Now, BTech, this time is between 3 to 4 years. If you go through the same time. Now, do you think in 4 years you can make from 85,000 to 150K? Do you think it's possible? Impossible. Unless you own your own company. You see this? Most people miss this. Most of them miss. The guy who wrote the book with me, he did PhD in 2.5 years. He's Chinese. So most of my students make 150. That other paper, the Travis, he got 145 in 2009. He's the director of a big robotics company, probably making millions. So why people don't go for PhD? India needs a lot of people. Yeah. So somebody told me MTech students get paid, that's all crap. I'm telling you right now. So if you don't negotiate, otherwise why would you want to go for a master's? So there is a problem. Of course, the salaries also vary with the skill set. Salaries vary with the skill set. So you got to have the skill. If you don't have the skill, naturally you can negotiate. Keep that in mind. Okay? So I'm not talking about these salaries, I'm not talking about Amazon or Microsoft. I have students, Google, Microsoft. They make even more. They're more than me, what they make. I have one guy in Amazon, he makes close to $500,000. He graduated in 2018. He did that cyber defense, I'll show you. Yeah, network control systems and cyber defense. So, I'm positive the same. It's not any different. So, just because you got an MTech, you shouldn't be expecting lower salary than a BTech. There's something wrong if you are saying to me, okay? So otherwise, why would you do PhD, right? Now, what are the other benefits for PhD? You don't get laid off. It's very rare that you get laid off. They don't hire that many PhDs. At the same time, they don't get laid off. So I'll give you my university statistics. Every year, we graduate about 800 undergraduate students across the campus, all different departments, okay? I would say about 250 masters. You know how many PhDs the university graduates a year? How many? Just guess. 40. You look at the comparison. Okay? So these are all the records. If you go to our department website, it shows you how much a PhD is making, everything. We usually use the low number, usually. Okay, so I'm just saying that a lot of times students don't realize that, and because nobody tells us at that time. But PhD means, when you're doing PhD or MTech, right, you guys get paid less, or some of you probably not, I don't know, GATE usually pays them some money, right? But how much they pay in a GATE? Now, how much is now?
I think 12,000.
12,000? Huh? 12,400. That's not much, right? A BTech guy who gets a job, he's making, let's say. So that's only a temporary for 2 years. Remember that. That's what I'm trying to tell you. The same thing when somebody is doing PhD, the MTech person would be making more, right? But that's only a temporary. But the minute you get onto it, you will be far ahead. You will be far ahead than the person who just goes with the bachelor's. Okay? Yeah. But remember, while what I'm saying is true, PhD is not for everyone. Don't forget that. So in other words, you don't want to join a PhD if you don't have the inclination to work hard. And you probably have sleepless nights many times because things don't work in the mathematics. Remember I told you that so things won't work. And that's why I said today, out of 12 months, 9 months we spend time on the mathematics because it doesn't work always. Until you get up in the night and you find an answer. Okay? So that's where the no pains, no gain. Okay? Alright. This has nothing to do with machine learning, but right now, Pretty much everybody, every company is expecting machine learning. Whatever I talk to you, the temporal difference error, all that is machine learning. We are applying this for control. And you see that data, I kind of skipped. All that comes in as part of that. How much data you pick, what type of data that. I just told you, you use the temporal difference error. But that's how you select that. Yeah. So, if there are chances, take course on neural networks, maybe deep learning. Okay, those are useful. And I'm publishing quite a few papers now. We show a lot of methods now, which shows a significant improvement over all the other ones that they use in these big companies, that LLM, large language models and stuff. And none of them prove, we do prove that, so it's a positive side of it. So that's the benefit having all these mathematics and stuff. It's no fun. You think that it's no fun, but I will never leave that side of it. So the control has that very strong mathematical background. So you should be thankful to all the professors who teach you. Yeah, you go to computer science, they don't know crap about it. You know, they use somebody else's work and they just write a software code. What did I tell you? Learn how to write software. That's needed. But once you do that, you are much more powerful than CS people because they don't know about the systems. They can't write just software because they need software for many systems. Remember that. They don't have that background. You guys have. Yeah. So learn how to do a little coding. Just not MATLAB, C code or C++ or Python. Now Python is wide. So many know Python. Most of you know. There's only one hand. Learn Python. Okay? All right. Any other questions, guys? This is my 5-minute advice. This is fact. There's no bullshit in here. Yeah. Okay. So let's go back. So observer updates, we looked at it. And there are two flow charts, the same idea. This is the state feedback, this is the output feedback. And we do the same thing for nonlinear systems, and I showed you all that. So I'm going to skip here. Any questions here, guys? Any questions? This is what we covered yesterday, so I just went through quickly. But what I wanted to cover today is quantization. Okay? But we use the same concepts, Q-learning, and neural network. So we are going to go into the quantization. This is the quantization side of it. Okay? So every control system has this problem, quantization. Okay, I know we talked briefly when in the first class. So why do we need to look at quantized systems? Why is that important? Where does this quantization problems come in? Even without the network control system. So let's say you are implementing a controller for a practical system. So where does the quantization problems come in? All the stuff is in the continuous domain. So where is the quantization coming? Yeah. Huh? Yeah, ADC. So you always use either the A to D converter or D to A. Like she said, the controller is in discrete domain. The system runs in the continuous. So basically you need to have some sort of an interface, A to D, right? From the sensor to back to the controller, and D to A. Convert the digital value into the continuous so that it has a hold basically between the sampling instant, it keeps the same value. That's all it is. So this problem occurs even without a network. So quantized means you have a finite code length on the A to D DTA, and you always have an error, just like Taylor series expansion. Okay? So the quantization error typically is bounded, but it causes problems. If you don't use it properly, it can cause the system to become unstable. The same problem happens when you have a network. Because the network is always operating in the digital. Okay, just like the controller. You see? And therefore the sensor value, if it gets transmitted through the network, gets quantized. And then the controller generates the digital value and it goes through the network. It's okay, the digital. But then when it goes to the actuator, it has to be converted back into continuous. So there is the quantization process. You see? And I'll show you today, because of quantization, there could be problems. In some cases, you can make the system unstable, even though you design the controller properly, okay? A lot of times we ignore that value, we just assume that there's no error between the quantized value and without the quantization, because none of us look at that, okay? So we will look at a little bit about it and see what will happen, okay? So that's what that is. So you see that this is network control, unknown because of that imperfections, and we have two cases, linear and non-linear case. Okay? So here is a block diagram. Now you can see that in the block diagram, there are two quantizers. One is basically quantizer from sensor to the controller. Like I said, the controller is a digital. And the controller sends in digital, and then you have another quantizer here, which actually needed to convert that into continuous. And that's here, the main reason is the communication network. Now there is an ATD DTA possibly, but the communication network also operates in digital. Remember that. And it uses quantization. Now look at the controller equation here, guys. So this XK, Q stands for quantized. So the controller uses the quantized value. A lot of times we basically miss that. We assume that it is not, there is no error in quantization. You see what I'm trying to say? Whereas the controller is using the quantized value, not the value that the sensor provides. And that's what the difference is. And it causes problems. Okay, so here is a linear system. You have a network, and the controller uses the quantizer. So therefore, the UQ, you see, we used to say UK, but here it's showing as UQ. Yeah, the pen is, let's see if I can use this as a mouse. Yeah, still bad. Okay, all right. So quantization effect is inevitable in computer-based control. That's why I told you, even if you don't have a network, you're going to face this problem. Quantizer model plays a role in the control design. A lot of times we don't spend time in them. So there are quantizers called static quantizer. That's what normally we use. There the step size is fixed. Now I'm going to talk about a dynamic quantizer which was developed in early 2000. Okay, where the step size varies over time, and there are benefits for that. Okay, and I gave you some literature. You can see that dynamic quantizer originally was done by Leverzon. He's a faculty in Urbana-Champaign, got his PhD from Yale. And so, as early as in 1990, they developed what they call static quantizer and how that linear system is stabilized with quantized state feedback. So, but dynamic quantizer was done with nonlinear control ideas, so they assume that the dynamics are known. So what I'm going to present is what happens you take it to the unknown case, when the dynamics are unknown. You understood that, right? That is the difference, okay? So here there is stability analysis but no control design. So here is the background, like you can see that you have the controller, UQ, so that's what I'm doing here. With unknown A and B, here is the terminal cost, here is the cost to go, and two quantizers, one for the system state and the other one for the control. Control inputs based on the quantized state, that is UQK is that KK times XKQ. Now remember all these chapters before, we used XK. So here we are now talking about a quantized value. So what I'm going to do is, I assume that the network has no losses, but I'm going to use the quantized value but no losses. Remember, these are different aspects. The packet losses and delays, we already talked about it. No, you can still have a stochastic, because you can still add the noise, and you can still make it as stochastic. Otherwise, it becomes deterministic. Yeah. So in the book, actually talks about that. Look at the book; it does talk about it. One of my students did the quantized system, but that was deterministic. Whereas in the book, we converted into stochastic. Because in the original work we did with the student, we assumed that the network is lossless. Where we didn't have the, delay and stuff. Whereas in the book, we converted that into expected value, that is with loss. You can do both. Okay? Any questions here, guys? What about quantization? Okay, so it's 11 o'clock, we're going to stop, right? We have tea. Very good. Very important. So how many of you watched the match yesterday? Yeah, that's a big deal, right? There's more to celebrate, maybe that's the tea. All right, guys, we'll see you in 5 minutes. Okay, bye. have a quantized value, because so far we were using u of k, right? Assuming that there is no quantization, but with the network you also get the quantization effect. Now, the professor asked me earlier, what is lossless? Because lossy and lossless we use in electrical engineering. The same idea. Here lossless means information loss. So whenever you have a network, you have packet loss. So you're losing that information, therefore lossless means you don't have any packet drops or you don't have any delays. Remember that. Got it? So the same idea, they also use lossless. The same terminology. Okay? So you see the control input here, you are using the quantized state value rather than x of k. So that's the difference between what happens, unfortunately. So there were questions about what is quantization. Now, remember, and how is it different from when we take a variable like a Euler's method, you convert a continuous variable to discrete. Now, mathematically, you won't see any quantization error. Okay? But there exists always a quantization error that comes from the hardware. Remember that. That's the difference. Like computers have finite word length, right? There's a round of errors. But when we do mathematically, you ignore all those. But in practice, when you're implementing it, you will see those. A lot of times we ignore that, and that's what I'm going to show you. You really can't ignore those. See? Alright. So here is the quantized stuff. So you can see that the original value, and here is the quantized value on the y-axis. Now you see the dotted line, a straight line. That is the ideal quantizer called the mathematics. So basically, that's a linear line which says that based on the current value, you get a quantized value. So there's no loss. You understand that in the linear line? That's what mathematics does. But in hardware, you see that there's a step function. That's where the hardware does it. Remember that? Okay? Now guys, you don't have to copy these slides, right? You will be given those slides. If you register for the class, you will get a copy of the slides, right? So you want to pay attention to what I teach rather than busy on taking. You can take notes if something is not there, okay? So now you see this here. The step function is the quantized value. And that quantized value has an error. That's number one. Number two, the quantizers have a saturation. You see here, m is the maximum value minus m is the minimum value. Mathematics says there is no saturation. That's in the idea of quantizer. But there's always going to be a saturation based on number of bits. If you only have 4 bits, you can only express so much value. Anything above that, you only get value of m, not anything. You see what I'm saying? So this is where that saturation plays a bigger role in there. Okay? So the drawbacks are, even though the quantized error is bounded, the bound can be large. We also have saturation. Anything above this m gets truncated to m. And these can cause serious problems to control. You understand that? Because you're asking, let's say 5 Newton meter, because of quantization, you may be getting only 3 or 4. So there is a problem. You see what I'm saying? There is a problem. Now we also will talk about actuator saturation later in the nonlinear part of it. Actuators also have a saturation. Now if you have run a motor, let's say they'll tell you the motor runs at 1500 RPM, right? But even if you increase the voltage, it won't increase the speed. It stays there at 1500. So actuators also have an saturation effect. So we'll see that in the next part of this presentation, lecture 6, where there is an actuator saturation. Okay? So there are 2 things you will see in the quantizer. One is saturation. The saturation is you think it's a value above m, but m is the limit minus m of m. There is also bounded quantization error within m, and that's expressed mathematically is if norm of z is less than or equal to m, then the error is given by that. If z is greater than m, then the error is given by that. And actually, it is, these are standard equations. You can play with them, okay? So now, we are going to go into dynamic quantizer because static quantizers have problems and I'm going to show you the simulation. The MATLAB code you can simulate, okay? So what is a dynamic quantizer? So to overcome these problems, if something is outside that limit, I'm going to use what we call zoom parameter. It's a scaling parameter. That scaling parameter in the dynamic quantizer will push the system outside the range to inside the range. You see? And that helps so that you don't have the bounded errors. So that's one of the benefits of the dynamic quantizer. And the dynamic quantizer equation is given by this. So you have two quantizers, one in the state, one for the control. So you see that mu x comma k q of that's the quantizer divided by this. So we adjust that mu so that mu x comma k, that's for the state, mu u comma k, those are called zoom parameter. And the purpose of the zoom parameter is to eliminate saturation, shrink the quantization error over time. Okay? So normally in a regular quantizers, the more the number of bits, the quantizer error goes to 0. You see what I'm saying? So, but ideally, there's always the ADT to A converters or even the network has a finite number of bits. Okay? So this is why, if you remember, they say that this company came up with 64-bit processor or 32-bit processor. So those bits essentially make a difference for us. Okay? So the zoom parameter helps to eliminate the saturation, and it also helps to shrink the quantization error over time. Got it? So, and the way you compute is the quantization error, which is given by the E, x comma k is given by the quantized value minus the actual state value, and that is expressed in terms of mu and then the step size delta, and that is basically bounded by E m of x, the upper limit. And this is the control. This is also bounded by m, and we are defining mu x comma k is the norm of x of k divided by that beta and gamma. Essentially, you can crank it up. If you crank it up, it pushes any values outside the range, it brings it inside, and it makes it nicely for you, like a nonlinear. So this way, the dynamic quantizer by Leberzon, this guy who developed that Leberzon, this quantizer eliminates the problems that you see from traditional quantizers. Do you understand that? Eliminates the problems that you see with traditional quantizers. Traditional quantizers are called uniform quantizers. And all uniform quantizers have saturation problems, which is dictated by the board length, which is the processor or whatever you use in your ATTBG. Okay? So there are issues with it. So now we want to use the optimal control policy with quantization. So we're going to start with linear systems. So what will happen when there is a quantization effect? And I'm going to show you in the derivation. I'm going to skip the derivation, but I'm going to show you. So we use the same idea I showed you, like a linear system. V of x of k, this is the finite horizon, x of k transpose s of k, where s is obtained from the Riccati equation. You see there is an expected value because we are assuming that, you can assume it's lossless, you can also add that, you have a network, you can also add it. Doesn't matter, okay? Now look at that, Hamiltonian. So you define the Hamiltonian. This Hamiltonian is nothing but the temporal difference error. The same temporal difference error is equal to 0. So the same thing, if the Hamiltonian is 0, that means optimality. Okay? Or the temporal difference error goes to 0 means that's basically the condition for optimality. Don't forget that. Okay? But in real life, you will have some error, and the goal is to drive that error to 0 by selecting that update laws and so forth. Okay? So now, and you use that Hamiltonian and you come up with that partial h over partial. Now look at that. Here I'm using the quantized value q of k here. Okay? So now what happens is if you take partial h over partial u q k, you end up in two terms. Now look at that. the first term is same as the Riccati equation. The control. Look at the second term. The second term has errors in the quantization errors in the state as well as the quantization error in the U. You see? So the derivation is identical that what we showed before, but now what you do is you actually write wherever there is x of k, you write it as E of error, quantization error plus that quantized value. So in other words, remember, so what I'm doing is I'm defining, which doesn't show here, so I'm defining the quantized error, let's say E x comma k is equal to some x qk or xk minus x of qk. So this is the quantized value and this is the real value. So wherever I have the state or the control input, the same thing. Here I have a control input. So I have u of k minus of u of q comma k, something like that. So what I'm doing is wherever I have a qk, I have to replace that by q comma k plus u of q comma k. So I'm replacing that. Because of that term, the error term coming in, you get an additional term here. You get an additional term. That additional term is because of the quantization error. So far, we didn't see that error because we assume that there is no quantization. You see what I'm trying to say? So you follow the same derivation, you get the same equation, and you get an extra term. Now, if you are using traditional quantizers, like I showed you, this term will not be 0. You see what I'm trying to say? That term will not be 0. So you get some error in your expected value of the quantized control input. Okay? You get an error. But if you use the dynamic quantizer, that error becomes 0. That's the difference why we use the dynamic quantizer. Now, does the current hardware uses it? I don't know. But this is done in 2000. Maybe they are using a dynamic quantizer. So that is the contribution of Leverzahn in one of his papers.
But in the current scenario with 64 bit, everyone have 64 bit. But
the error, you still will have an error, but it's proportional to the number of bits.
Quite small. I don't understand that quantization.
It is small, but what people have shown is it can still cause instability.
That type of situation, that type of problem.
Yeah, it is currently there. People don't, that's what we were discussing with some students, people don't realize it. In some cases you don't, and that depends on how fast is your system. That again comes in that perspective. If you, for electrical systems, the time constant is usually very small, like motors and stuff. Yeah, but whereas you take, look at the solid state, let's say for power electronics, they switch very fast. Oh yeah. Sure. But you understand the difference, right? It's real. It's real. In communication systems, power electronics, because they use those wide gap semiconductors and they have a very fast switching. Yeah, so, yeah, go ahead.
Another thing, reversion paper I have not seen, but dynamic controller, what is new something and multiply?
It is multiplied and they divide it and then they adjust the division. So they crank up, that's called zoom parameter. So what happens is if you have a value outside the saturation range, by cranking up the zoom parameter, it's scaling, you are trying to scale it, and you are pushing it inside the saturation of the quantities.
But overall you will change.
You will change. Yeah, you will change, but it still works, and I'll show you. It still works.
It is better than the saturation.
That is correct.
That has to be put
That is
in
correct. Okay, any other questions? You understood, right, what Professor was asking? So, I think the quantizer zoom parameter will help you to bring it within saturation, because when it goes to saturation, there will be large error. And so by adding that zoom parameter, you are scaling it basically. And when you're pushing it, it's got software scaling, right? Remember, the hardware has a problem. You're scaling it, and we do that in neural networks. And basically what it does is it puts you within that saturation range. Then you do that calculation, and it comes out, you multiply it by the scaling factor, and that takes care of it. Yeah. No, select. You select. Yeah, those are you selected. Okay, but what that equation 4.17 says is, if you have errors both in E due to quantization and in U, those error terms show up. And they get multiplied with all these E and A matrices. So that's how the error becomes significant a lot of times. And it becomes significant, it can also cause instability. That's the traditional quantizer. So in a traditional quantizer, the more the number of bits, the error would be smaller, but there will be always there, it won't be zero. But with dynamic quantizer, you can make it zero. That's the beauty of the dynamic quantizer that Liberzon did. So what we did was we took it and then we showed that it does affect your Q, that is the quantized value in this case. So if I use the dynamic quantizer, then my control input, the Kalman gain will be with respect to the original value. If I don't use it, I get some error, and that is the cause of the problem. You understand that? So this is the first step. There is no system dynamics. There is no, there's still a known dynamics here. So you start with that case. Why or how this quantization affects your control input. You understood that, right? So the left-hand side is the optimal control input. The right-hand side is the equation. This first term is same as the traditional term and A, B are known. The second term is probably added to accommodate the error in the quantization. Okay? Any questions on that? So this equation shows how quantization error affects the control input. Okay? Any questions? All right. So what it shows is, one is the Kalman gain doesn't change, whereas the control input uses the quantized value. Look at that, xkq. So normally, so far we are using xk. But the q stands for the quantized value because you have the quantizer. Understood that? So that's the difference. So we'll skip all that. So now what happened, remember this is a linear system, we did the same steps that I showed you. So pretty much you define the Q function, which is the cost to go with J of k plus 1. You can express that, I already covered it in the morning. So J of k plus 1 is A times X of k plus B times Q of k transpose. And you get a different Q matrix. And then you do the same adaptive control. And then the UQK is basically used as XKQ. This is guarded XKQ. And for finite horizon, DK will be time varying. Here we don't need the dynamics. So, but the only difference is the temporal difference error. Now a function of the quantized value. Don't forget it. Because you are taking the quantized value of the control input, you are taking the quantized value of the state. Because you have two quantizers. One from the sensor to the controller and the other one from the controller to the actuator. Don't forget that. So you are rewriting the same Bellman equation, but except that all these states now are quantized. You see what I'm trying to say? The approach is identical. Remember that as like a Q function. Now look at that. The only difference is the update law. We can't use the same update law that I used in the adaptive control without quantization. There is a huge difference. Look at the equation there. Now, how did we come up with that? From stability. It's not something that computer science guys gave me. They don't know how to derive that. Yeah. From the Lyapunov of stability. You see? So Lyapunov of stability. Wow, it's too loud now. Probably you don't need this mic, I keep saying that. This is one thing always my wife complained for last 27 years. I don't need a mic. She says that you need to slow down and calm down. So we have made sure that the walls are solid. Anyway, okay. So the thing is, you see all these different terms there? You need them. Otherwise, you can't prove stability. Okay? So you see that there is this EBQ. EBQ is the Bellman error. E and K is the terminal constraint error. And these terms are added to accommodate the saturation and stuff. And the basis function essentially is the time varying n minus k. I already explained to you, it has to be n minus k. N is the final time, k is the current time. So basically, this is a finite number of time instance. So you can use approximation if it's in your own network. Otherwise, it's a problem. A lot of people, control people say, how can you use time over a compact set? Okay? So this process is the same, and you see that how complex is that, and alpha theta here are the learning rate parameters. Okay? Are the learning rate parameters. And you see those zetas here? Zetas essentially are basically the history values. Remember that? So using the history, like in Bellman error, I skipped here, all that stuff. Okay? So your update law, theta hat, which is same as g hat in the previous paper. So here we are writing as theta hat. So you see that the g hat is theta hat times phi of k times z bar. So the theta hat is basically same as that g hat, and you have a completely different update law in order to show the stability. Okay? And here is the flow chart. Now, the only difference is, if you look at the flow chart, you initialize the value function, the initial controller, which is the admissible controller. Here is the system dynamics. You take the quantized value, state quantizer. So here I'm using dynamic quantizer. Okay? And that quantizer gives me values. Then I'm constructing the Bellman error and the terminal constraint error. Once you construct it, then I'm updating the G hat, okay, which is basically same as the H matrix, okay. Once I construct the H matrix, I unpack it, then I compute the control input here. I'm computing the control input. Then once I get the control input, I use the control input quantizer, which is another quantizer, and then I get the control input value, which goes to the actuator. Any questions here? Any questions? So the flow chart should tell you. Now, in the past few classes, we don't have the quantizer blocks. That's the difference. You see? And we ignored completely the quantization. Okay? All right. So then the question would come in is, really do we care? We have hardware which is 64 bits and so forth. Okay? So here are the proofs. I'll skip that. So let's go back to the batch reactor, because we are so fond of batch reactors. So you have the A matrix here, and this is the B matrix. This is discrete time, after discretization. Okay? So here we are not looking at the network aspects. The network is assumed lossless. Okay? So you see that if you look at the poles of these equations, I put the poles. One pole is at 1.22, the other pole is 1.0064, the third pole is 0.6, the fourth is 0.42. Now, is this stable or unstable system? Because a couple of poles are outside the unit disk. It's an unstable system. So inherently, batch reactor is unstable, just like the inverted pendulum. You understand that, right? So remember, I told you the optimal control, when you are designing an optimal control, that means it also stabilizes it. It goes without saying. In addition, it also optimizes it. That's the benefit over the traditional stabilizing controller, pole placement. Got it? Okay. So now I selected, in this case, Q matrix, weighting matrix, or Sn is equal to identity. And you see that the quantized value, the augmented state, has the quantized state value and the quantized control input. Okay, I'm only using one value. I don't take the history here. I'm not doing the history. Now, this is the initial state is considered as a deterministic, and K naught, the initial admissible control value, is given by that. The sampling interval is chosen as 0.1 seconds. Now, moreover, to obtain the ergodic behavior. Remember that? Monte Carlo simulation runs with 1,000 iterations were utilized. So 1,000 times I ran the simulations and they get averaged. So you see that because this is treated as the stochastic system. So don't forget that. For deterministic system, you don't have to deal with it. Only for stochastic system, we have to do the Monte Carlo. You typically vary the initial conditions. People also do that for deterministic because I don't know about some of you who are students here. My student gets one initial value, he shows nice result and says, I'm done. So I tell the student, you vary those initial values, initial selections, and tell me when it doesn't work. And he always comes back and says it works, but then I say, okay, pick a value which is outside the initial set and it doesn't work. So you have to pick a lot of different values and find where it doesn't work, where it works, and then you have to do it. Now, why is that? Because if you look at adaptive control, I don't know whether you have noticed this. The adaptive controller for a linear system is non-linear. How many of you know that? I know some of you took adaptive control. The adaptive control for a linear system is non-linear. So that's the learning part. Remember that. Okay? Now, do I know when I was a student? No. So, the adaptive controller for a linear system is non-linear. And why is it non-linear, guys? For a linear system. So, or the closed loop system of a linear adaptive system, adaptive control system, is non-linear. Okay, why? Why? How many of you said you have taken a course on adaptive control? No one said. I know. So if you have taken the course, did you guys do linear adaptive control or you had some non-linear as well? Mainly linear. That's what I was asking. So remember, you have a linear adaptive control, linear system, then you design an adaptive law, right? But then you compute the closed loop dynamics, error dynamics, which has it comes with a theta tilde, which is basically the error in the parameter estimation error. So why is it non-linear? Why is it non-linear? See, that's the learning part. Because, you remember you're using that update law? That update law is non-linear because it multiplies. You see here, it multiplies two state values or temporal difference error and the basis. So therefore, because it has the product or a square term in some cases, so the adaptation law is non-linear. And the closed loop dynamics become non-linear. Therefore, even though the original system is linear, the closed loop system becomes non-linear. That's why we use Lyapunov stability. How many of you knew this, guys? Let's be honest. Those who took the adaptive control, do you know that? Okay, this is the difference. I teach a class. Yeah. My own instructors never told me this. I had so many good instructors. No, very good instructors I have. But no one. No, this is important because if somebody asks you in one of the interviews, yeah, I ask people, the closed loop adaptation law, is it linear or non-linear? They can answer. So think about it. Okay? So that's something you learned today. All right. So optimal control design flowchart. So here is the simulation stuff. We have taken a discrete system. So basically for quantizer design, beta is 0.9, gamma is 0.9, alpha is 0.01. We have done that. Now look at the results. So the system response and control input, right? So they are converging. They pretty much converge. There are 4 states, and when 4 states converge, the control input converges, right? There's no fun. So somebody is still wondering, why do I need the dynamic quantizer, right? Okay. So now I have plotted, there are 2 cases in this figure. Quantization error for dynamic quantizer with R equal to 4. So there are bits, 4 bits. And quantization error from a traditional static quantizer with R equal to 4. Now look at the difference in plots. So in one case, dynamic quantizer, you have a little error, but then it converges to 0, right? Look at the static quantizer. What happens after 10 seconds here? Huh? It diverges.
So how to take the value of beta and gamma for the dynamic?
You just select it. Okay, and basically stability, you pick those values so that it's within the stable range.
That means we can go for the trial and error.
No, we use, that's what we do, because we don't know exactly the region of stability. We still use the trial and error. Yeah. And in this case, I'm positive the student found the right result, which shows nice results. I already told you that. That's what they do, remember? So I'm positive he wants to show this, so I asked him, okay, do this, I want to see. And then I'm positive he showed me this, but he basically picked those values. Okay, so you can see that it does how it can become unstable, right? Now in this case, errors from traditional dynamic quantizers. So what I did, I want to vary the number of bits. So I want to see what will happen. So remember I told you, as I increase the number of bits, I want to see the errors in a traditional quantizer also would come down, right? And that's what happens. But there's a difference. You see, this is the result A, is the quantization error from traditional static quantizer with R equal to 8. So when R equal to 4, it blows up. When R equal to 8, you have initial errors, but it converges. Now look at the other one, the dynamic quantizer. It's perfect. You see? So there is as you increase the number of bits or the quantization bits, essentially you see that the errors are much better than even our own quantizer with 4 bits. And that's what I was trying to tell you. As you increase the number of bits, the quantization error would come down, and we know that the error is typically bounded. But because of saturation, that bound can be large. You see, that bound can be large. All right? Okay. So now we look at the optimality. Remember I showed you the Bellman error. So here you see the Bellman error is driven to 0. That shows that it is optimal. And also the terminal constraint error goes to 0. So this clearly shows that we had the Q-learning coupled with the quantization. We are able to study the quantization at the same time. We are able to study that we are getting an optimal control design. Now the last plot is the difference between the known dynamics case and unknown dynamics, Q-learning. Okay, remember that. So what I did, I assumed the dynamics are precisely known without Q-learning, and then I plotted the cost. And then I did with the Q-learning that I showed you. And I'm comparing the difference. So you see that initially there's a difference because it starts with some initial value. But you see how quickly that it goes to 0. So you see how quickly it goes to 0 here. Initially there's a large value based on the initial value. But then it converges over time, and within about a second, the errors go to 0. So that difference goes to 0. That means that the system, Q-learning, learns the dynamics and generates the optimal policy pretty fast. Now, that also depends on the selection of alpha, theta, and all. So I'm positive the student probably tried to, make it better. You see what I'm saying? So if you change the values of alpha, theta, you may get a long error for a longer time. But in general, it converges fast. Any questions here? So we studied what is quantization, what is static quantization, how it affects the control input and the state, right? We need two quantizers, one for the state to controller, other one for the controller to the actuator. And we saw how it changes the mathematics in the control input. That's very critical. See, that's why papers get published. You have to have a mathematics to show why it affects and why is it important. Then, basically, I went back and I used unknown dynamics case because some people have done known dynamics, we are doing the unknown dynamics. We use the Q-learning. And then even with Q-learning, we are able to demonstrate if I use a traditional quantizer, things can go unstable. You see? With the number of bits. So as you increase the number of bits, 1 second, we have shown that even the quantizer, traditional quantizer becomes, and so we know that happens, but we want to reaffirm. And that's what we have shown. Whereas with the dynamic quantizer, we don't have the problem. We don't have the saturation problem. Okay? Yeah, go ahead.
So, that's what I was asking. If we have a 4D system and 8D system, we can work with the unknown dynamics and with static quantizer. So, for those bits, I mean,
The number of bits, as you increase that, you can make it 0. Because you are, you know, what you saw the saturation range. The M is the saturation range. When you increase the number of bits, you are shifting that M. You see? That's what it is. Any other questions? So it has to be that simple at the end. All right. So no questions? Okay, so we'll go a little bit. Okay. Okay, here is another example. So this is a different system, A and B. This is a more simplified system, and you see that the parameter selections. And here is the basis function. So here it converges nicely. Convergence is guaranteed. In this case, there are only 2 states. And here, advantage of the dynamic quantizer. Now, why did we do that? I wanted to see if I change the system, okay, do I see the same results that I saw in the batch reactor? This is the other thing my students do. They always start with a simplified system. I keep telling them you have to pick a realistic system. Because they think that you have to write a code. In the batch reactor, the state vector is 4 by 1. In this example, this is a toy example. There is a 2 by 1, so they quickly do that, okay? So this is their first example. The other one is, I have to tell them. Now look at that. So this is the case 1 r equal to 4. Fewer number of bits leads to instability of the system with the traditional quantizer. So we saw the same problem. While stability is ensured by the proposed quantizer, you see an error initially, but it converges. Now you increase the bits, r equal to 8. Okay? So you see the traditional quantizer, the error is bounded. But there is an error. There is an error. Whereas with the dynamic quantizer, actually the error goes to 0. So the same kind of conclusion that we did for the other system also was true. The only difference is this is in color, the other one is a little black and white. Because this was used in the papers. And this is the first thing. When we wrote the book, we basically might have added the other example. And you can see the Bellman error goes to 0. That shows that the optimality is attached. And the terminal constraint error also goes to close to 0. And therefore, the terminal constraint is also satisfied. And then you want to see the difference between the 2 costs. Consistency for the optimal design, and you can see that the error also goes to 0. That shows that the case of unknown dynamics converges to the case of known dynamics over time, which shows that the Q-learning is really working. Got it? All right. Okay, so I'll start with the intro. We have 5 minutes, and then I'll start. So now we are going to go into nonlinear. So far we used a linear system. So for linear system, we are always using what learning method? Q-learning, don't forget that. So for nonlinear, we are going to use what? Neural networks, because you want to approximate those nonlinearities. And then we use actor critique or one of those neural networks. So don't forget that. So when the plan becomes nonlinear, control design will become more complicated. Got it? Moreover, optimal control design for very difficult to solve because of HJB equation. Okay, so you can see this is the paper that you guys have simulated. Okay, and so these are some of our papers. The one is the iteration-based solution. The other one is the time-based solution. So now traditional optimality is if I have a nonlinear system in discrete time, and here is the value function, here is the terminal constraint, here is the cost to go. This is a finite horizon. So, and here is the terminal constraint. The optimal control policy is given by R inverse G transpose. That means you need to know the G. Partial V star. V star is a solution for the HJB equation. Okay? And here is the Bellman equation, which is the recursive equation. Don't forget that, okay? So, two issues. Partial dynamics needed, because if you look at this, in this particular case, the Travis example, remember I gave you the code yesterday, I think Dr. Vera. So here you don't need F, but you need the G. So here, we want to relax both, I think. That's why, and then one time step ahead information here. So basically you are approximating a neural network for U and maybe one neural network for V. You got it? So we are using two neural networks. Okay? So in order to estimate the dynamics, the first step is to use identifier. Now, those people who have taken adaptive control, what is the purpose of an identifier? What is the purpose of an identifier? Huh?
It will give the input to the handling formula.
What is the goal of an identifier? So the goal of an identifier is to estimate the system dynamics. There is a controller called indirect adaptive controller. Indirect adaptive controller, you use an identifier, you estimate the dynamics, and you use that information in your controller to design the control. Okay? So the identifier here, I'm using a neural network identifier, and what I'm doing is I'm using one neural network to approximate both F and G, and then I'm defining an identification error, which is the measured state versus the estimated state, and then I'm using history. Here also I'm using history. Look at that. Okay? So this is what is called data-driven control. So all these Chinese guys, they write a lot of papers. So they call this as a data-driven control. So basically they take the history. In discrete time, always we used history. But we never call data-driven control. Okay? So this is all this called data-driven control, data analytics, machine learning crap. There's nothing new about to me. Okay, so all this is stuff, okay? So you see that it's a data, it says x of k minus 1, x of k minus L. So all these previous values of the state and whatever, right? So then you pick up the identifier. Here is the update law for the identifier. And we show stability, that's why we pick that. So first we use an identifier. Identifier generates f hat and g hat. Got it? Now why do you need f hat and g hat? The g hat is required here. You see that there's a g there, so you need the g hat. Otherwise you need to have another neural network. So either you use two neural networks in actor critique mode, or you use an identifier and generate f hat and g hat, and you replace wherever there's f with f hat, wherever there's a g with g hat. But then the difficulty is in the proof. It's not just replacing that g with g hat, because g hat has w hat, and when you prove it, you have to bring all kinds of problems you face. Okay, so that's mainly the difficulty. So you do that. In this case, I'm approximating the value function v. You see that I'm using one neural network. Here is the terminal stage. Then I'm generating the Bellman error. Okay, I'm going to go through quickly, but we'll go back again. I'm generating the Bellman error. Now look at the Bellman error has got the v hat and all that stuff. Then I'm computing the update law for the critique. The critique uses the Bellman error. Bellman error is measured. Now there is no quantization here. So I'm doing first without quantization. You understand that? I'm doing first without quantization. And then we'll see what happens in the quantized case. So I do the terminal constraint error and then I use the total error to tune the critique weights. Now who told you those update law? It comes out from the Lyapunov stability. Understand that? So that takes a lot of time and we are skipping all that stuff. Now the control signal is also by another neural network, second neural network. Now in the control input we have to tune. So that was a long time we were breaking our heads. In 2000, so we were the first ones to come up with how do you tune them in real time. So this U tilde is basically the U1 value from one way, the U2 value in a different way, and then we take the difference because you measure U1 hat and you measure the U2 hat. So this is the two different ways of computing the optimal control input. That's a very smart thing. When my student, he was probably spending like 3 months breaking his head trying to come up with how do we find a measured value. And these two quantities are measured. These two quantities are measured. So U1 hat is given by the output of the network. U2 hat is computed by taking the G hat and taking the partial V hat or partial X of K plus 1. So U1 hat and U2 hat are measured, but it's computed from two different ways. And we take the error and we are using to tune the actor weights. Is there a different way? No. The entire world is following this. So unless you come up with some other way, right now this is the way. Okay? So now we are tuning the actor and here is the flow chart. There is no quantized system. So you have the initialization. You update the identifier, use the information, you update, you get the value function, you basically critique updates, you compute the control input, the actor updates, and then you check the time whether you reach the final or not. Because your actor updates, you compute the control input, you apply that, and then you increase the time to K plus 1 and you go back. Okay, so this is the nonlinear neural network control for a nonlinear affine system. Okay, now I hope I have an example. Here are the proofs. So now let's take a two-link robot arm. So two-link robot arm, these are the dynamics. This is f of x, this is g of x. Okay, so two-link robot arm is a classical example for nonlinear system. It's a very well behaved. And this is an affine system. So most of you know what affine is? Okay. I think I see only one person, nobody is really staring at me. How many of you have taken nonlinear control? Okay, so did you guys learn about affine and what is the other one? Huh? Non-affine? No. Yeah, non-affine is there, but I don't think you might have studied non-affine. What is the second system? These are called class of systems. One is affine, what is the other one? Okay. Put a mark and find out. Homework. Okay? So this is an affine system. Okay? So the sampling interval is 1 milliseconds. The alpha is 0.9. The value function alpha is 0.01. Here is the other one for 0.1, and here are the values and so forth. Okay? And so you try to simulate it. So all nice results, right? You see that system response, they converge to 0. Very quickly the control inputs converge, but this only converges when the identification error converges. Look at that. The identification error for that f plus gu, they converges. Okay? And basically, you can see that the Bellman error, it converges, the terminal constraint error converges. This is the critique weights. See, critique weights are converging as well as the actor weights also converge. So this example shows you don't require F, you don't require G, and you're using 3 neural networks, 1 for identifier, 2 for the other, okay? So then, I'm going to stop here because it's 12:05. And so you can do the same thing tomorrow, output feedback, and then we get into the contest system. All right? Any questions, guys, quickly? Any questions? So tomorrow morning, I'm going to ask you some of those quiz things. So make sure you come back with some answers. Okay? So otherwise, we'll forget. Any questions? Okay, I think it looks like everybody's hungry. So we'll meet at what time? 2 o'clock. I think he already sent you the MATLAB code. So my gut feeling is we're going to meet. I won't be doing anything. You guys will be doing all the stuff. Okay, that's how the tutorial is. And you're going to go and show me what you got. So you're going to run the MATLAB code, right? The code is given, right? So whatever we covered, you go back and do you have the schedule on there? What is basically in the tutorial? There should be a printed stuff, right? Yeah, so you only run that MATLAB code for that particular set of systems and you play with it. So I won't do anything, it's all your work, right? And you learn from it, okay? So everybody has a laptop? I'm positive now, right? So you guys have access to MATLAB? So did anybody try running? I know these people have done, that's why they are in the front bench. So I'm asking for those who are in the back, did anybody try the MATLAB code? Doesn't look like. That's what you guys are going to do. Did you try? Huh? Okay. Yeah, so at 2 o'clock, you guys are going to do, okay? All right, guys. We'll see you. Have a good one. expenditure, not as a amount of grants. So they want to see the grants, if you need to get this, there's a important, right? Otherwise, we need your attention. I know there are a lot more people missing. So I heard from Dr. Bera that you guys had the assignment 1, right? So I think that's good that it was his idea, and he and one of his former students, and they were very nice. They created this, and it's not that hard. So I was thinking changing the A and B matrices, but what they were doing is they really changed also the dimensions of the vector, because unless you do that, you're really not going to go through the code and make some changes. So I think I was very happy, honestly, okay? And the other nice thing they did was they kind of broke that whole problem into multiple steps. Like you see that first is simulate with a discrete time LQR, the standard LQR, where you need to know A and B matrices. So DARE stands for Digital Algebraic Riccati Equation. Okay? So I think it's not, so you need to know what is the syntax of DARE. It's already there in the code. But I'm just saying that. So once you know the dimension of the system, you make sure you understand what that is, okay? There is a noise there, and the white noise, it says you pick it and you have the command in the MATLAB. And you can pick between 0 and 1. All right? So if you look at the first problem, it says simulate the discrete time LQR for the batch system with some random delays. Then simulate the optimal controller. Okay? And then you basically add the random delay and packet losses. You do the suboptimal control using AZ/BZ. Okay? And then you assume AZ/BZ are known, and then you try it so that you can contrast the what happens known and unknown case. And then unknown. So I think they kind of nicely, we went through that in these things. They nicely kind of split each of those questions. So I think this is a very nice way to look at different cases, distinct cases. So the only thing that changes were the dynamics and along with that the dimension of the state vector. So other than that, everything is the same. It shouldn't be that hard for you. I think how many? You have 2 problems?
I gave
4, 5. Do at least 1 or 2. I think that is sufficient. Keep doing that. Okay? So I'm going to pass it to him. I think the credit goes to him. Thank him that, So I'm going to pass it, yeah.
Okay, good afternoon. So you can already I have shared this particular assignment sheet as well as the MATLAB code. Now I will going to help you that how you will start, and once I will explain the things, I am not going to explain everything. I'm going to just help you that what are the things you need to care about, and then gradually you will find that you are able to do the things what we are asking for. So if you see the problem 1, in problem 1, dynamical system in continuous time it is given, which is a batch reactor system, and I think several time you have seen this dynamics in sir's slide. Okay? And now what we wanted to do, here you will find that this system is affected by a white noise. Okay? And ultimately we want to implement the Q-learning based adaptive optimal control to stabilize this. Here some mistake is there, it will be not the inverted pendulum, it will be the batch reactor considering unknown system dynamics. Okay. Now what we want to do that, generally if you want to solve a big problem, the advice is that don't jump into the problem directly. First, you think the problem can be solved in a modular way. Small problem you solve and add complexity stepwise and try to solve. Then you will find that ultimately at the end you are going to, or you are able to solve the problem what you have targeted for. Don't think that, okay, first I have to implement the Q-learning based adaptive optimal control. Don't think like that. Okay, so we will do it stepwise and we will add the complexity stepwise, and then we will correlate with the theory, and then we will able to do it. Okay. Oh, fine. So that's why the first problem what we are going to do that simulate the discrete time LQR for the batch system without random delays, packet losses as well as the noise. Okay, nothing is there. Simply you have x dot equal to ax plus bu, and now you want to implement a discrete time LQR to stabilize it. So then how you will proceed? Can anyone give a hint about that, how we will proceed? Suppose this is a continuous time system, but now we want to simulate the discrete time LQR to stabilize this particular system. So how we will proceed? What will be the first step you are thinking about? Exactly. So then you need to fix what will be the sampling time you want to sample this particular system to make the system discrete. So do you know how we can discretize a continuous time system? You know that one. So then here in your code you will find that the whole problem is also segregated in several cases. You have to extract those cases and then one by one you have to simulate. Okay? Like I am going to the MATLAB code, then only you will be able to understand what I am trying to say. Let me open the MATLAB code. Here the MATLAB code what I have shared, this is the MATLAB code I have shared. You will find for the problem 1. You will find that one folder is there which is called problem 1, and inside the problem, let me show the folder also. There should not be any confusion. You will find that this is the assignment 1, this folder I have shared with you, and this is the problem 1 folder. Okay? In problem 1 folder, several other files are there. Only you concentrate on problem underscore 1, this MATLAB file. You open that. Okay? Rest of the things you will automatically will able to understand what are other supporting files are there, what is the need of that. Okay? Eventually you will come to know. First you open problem 1, that file. Opened? Okay, very good. Now you see what I am trying to say is that sorry, you will find that the system you see is defined here, AC and BC. This is the system, continuous time system. So C stands for continuous. Okay, so this is the system where the continuous batch reactor system is given, that is defined here, AC and BC. Okay. Now you see, after that it is written discrete time batch reactor for NCS augment state system model. So now you see, whatever the suggestion you are going to give me, that sir, we have to select one the sampling time and we have to discretize it. So that's why you see TS is the sampling time, and TS has been defined at the beginning of the program, and it is written, you see TS is taken 0.02, and it is written also the sampling interval. It is already mentioned, so you will be able to understand everything. So now with that we are calculating the discrete time equivalent of that continuous time system, which is written as AS and BS. And you see here, you know that to calculate A, you know that it will be, what is the formula for to calculate the discrete time case, the system matrix? AT. It will be exactly, you see, same thing it has been done, it will be for AT. And also there is a formula for B. Here, actually, if you see the formula for B, one integration you have to do. And for that, one function is declared here. So it is the way it has been done, but it is not mandatory that the same thing you have to follow. If you have other idea to discretize it, you can do it. But main thing is that you have to calculate the equivalent discrete time system matrix as well as the input matrix. Do it first, okay? And once it is done, then you will find that here I am saying what you have to do. These things are for the first case, it is not required. What it is required is, I am telling you, you see here, you see in green it is written that original system without random delays and packet losses with optimal control input. Means we are not considering any kind of delays, any kind of packet loss, only we are going to stabilize the system using discrete LQR. Okay, so that's why first here the Q and R matrix are defined. You can play with Q and R also, but that you will do later on. But now just Q and R you take, and here you see here this line is inactive, but you can open it now to calculate the gain K1. And here you see DARE we are using based on 4 things. What are the 4 things we have given to the DARE? That is AS, BS, Q and R. With that, you open these figures and see the result, that whether this gain is working to stabilize this system or not. But for that you need, and now I am moving what I have done. We have separated the program for case 1, case 2, not the whole thing. Now I am showing this one. You see, this case 1, only I kept whatever is required. You can do also that one. Whatever the first problem to solve, whatever the codes are required, that part only we kept. Rest of the things we have deleted, but for you, if you do not want to delete, just you make it comment. That's all. And you see whether it is working or not. Rest of the things to you, you do it and tell me that whether your code is running. And here only one thing I am telling you to do this. You see this line I make it open, but I kept this K1 comment, and here I am declared K1, okay, the gain of the controller. And now with that gain, we are applying this gain to the system, and then we are doing the plot, and you see that what kind of plot you are going to get, whether the system is stabilized or not. Okay, done? You will find that if I will run, you will find that the 4 states here, you see K1 is calculated by MATLAB, and this is the states you are finding that it is converged. Okay, so rest of the things I will not tell. This is the first thing I told you. Now you will find that in the same program case 2 is also there. You see how the case 2 is formulated, okay, and then subsequently you try the other modules also. I will help whenever it is required, but try to do by yourself only. And my advice will be to split the program case 1, case 2, case 3, case 4, case 5. You see, I have splitted the program for here. If you see case 1, this is for my case 2, this is for my case 3, this is for my case 4, and this is for my case 5. Okay? And other auxiliary files must be inside the folder of each cases. Don't delete it. Okay? Fine. So let us do. And let me see. Before doing the things, one thing I just wanted to tell you, just you try to understand. You see, when you are going to do the number 3, what it is saying that simulate the NCS with random delay and packet losses using suboptimal control, which uses the mean value of delay to calculate the system model AZ and BZ. Okay. So, can you remember in Sir's slide, Sir told that when you are going to consider the random delay and packet losses, how to calculate the A-B matrices? Can you remember that? I will show you. For your convenience, I will show you that where it was. Let me show you such that you can recollect it and you can do it. Then only you will able to understand that the correlation between this program and whatever the theory has been taught in the class. Somewhere here. You can also find it, then it will be easy for you to understand. Oh, it was in introduction only. I saw that one. Now I can remember it. Yeah, this one. You see? How to calculate AZK and BZK considering the delay and packet losses. Okay, this formula will be useful. Then only you will able to know how the D bar is defined in your programming. Everything you can able to know that how to calculate. Suppose you have here, this is the particular slide I am talking about. This is a very important slide for, I think, every problem you will encounter later also. Okay, so x dot equal to ax plus bu, and then after incorporating assumption and considering the wireless imperfections including the delay and packet loss, the NCS can be represented by this. And now you see how the AB matrices are calculated and what are the other parameters are there. Because exactly this thing has been done in programming also, to calculate whenever the packet loss and the delay is there, how you will calculate the AB matrices for that case. And ultimately you will find that this will be the augmented state. That augmented state is also you will find in the program, that xk transpose, then uk minus 1, then uk minus d. Okay, so D bar, so these are the augmented states. So for your case also you will find that augmented state we have declared, and we have calculated AZK and BZK formula. You just check it and see your program how this particular AZK and BZK is calculated there for the problem number 3. Problem number 2 is not a problem, you can do that one. Okay, so now you continue to do the problem 1, 2, 3 subsequently, and you will find that hint is given inside the main program only. Every cases are distinguished, only you have to understand what is required, what is not required to run that particular case. Do it. So this is the thing I am talking about. You see, generating NCS augment state system model AZK and BZK. Okay. So this is the way we are calculating, incorporating the delays and packet loss to have the AZK and BZK. ये अभी देखो I will request you to see the corresponding slide also, because you see all the theories you cannot remember. So side by side you consult the particular slide, you try to identify that which slide is important for you to understand that particular program. Then only it will be clear to you. Take your time, that is not an issue, but you try to understand it. And another important thing you see, if you want to do the last part, this slide will be useful for you. You see, if you want to do that, simulate the NCS with random delays and packet losses with optimal control, basically this one we want to implement the Q learning based adaptive optimal control. That is the final goal. If you want to do this one, then you require this slide. I'm telling you which one. That is the Lyapunov stability Sir has shared or I have already shared. This particular slide will be useful where you see how this Q function has been generated. Q function has been generated, and this is the formula has been used there to have the Q learning algorithm. Okay, so this will be useful for you. Here you read this particular assumption that Q function, how it is linear in parameter, LIP. If you read this paragraph, it will be sufficient to solve that particular problem, because here whatever the way the weights are taken, exactly the same way the weights are defined in the programming also. Because if you see the weights to be chosen, here you see the hint has been given. What the hint has been given? You see, select the regression function for the Q function W1 square, then W1, W2, and you will find that one additional that is file is there in that folder where this function's regression function is defined. Okay, so that you can identify. So I'm keeping this particular slide open such that you can have this. If you
Sir, function here is activation vector.
yes, exactly. You see, these W's are required to be defined, and that is defined in their activation function. Yes, that is a model-free Q learning, where the models are not known to us. Those who came late, for them I am telling you, MTech people, you will find that we are dealing with the problem 1, and your MATLAB folder, you will find that one problem 1 folder is there, where you open the M file related to problem 1 only. Other are auxiliary files. Main file is the problem 1. And there you will find that the whole program is segregated with different cases. Case 2, case 3, you see. You split that according to the assignment 1. You see, it has been written that first you do the programming only with the discrete LQR. So you split the program case 1, case 2, case 3, case 4, case 5 from the main program, that is problem 1. You will find that it is all the programming are merged there. You have to split it by understanding. Any unstable case you are finding, or all cases you are finding that the system is stabilized?
So far we have seen 2 cases.
2 cases, okay, fine. Case 3 you go, very good. Case 2 is also you will find that it is stabilized. Yes, good. Then you go for the case 3.
Case 3.
Sir, in case 2 we'll use the K1 obtain the first.
Yeah, same. Yeah, that's why in your programming it is written whatever the K you have calculated in the 1, that same K you use for the solving problem 2. Means the case 2. And I will advise you, if you find new command, what you have not known earlier, you take the help of MATLAB to understand that. That will be a nice thing, that you are going to learn a new command, what you have not used earlier. Several new commands are you will find in that particular problem. Okay. 1 second. No, here actually you will find that here this is the delay we are initialization. Yes. Yeah, this is the program. Yeah. Yeah, exactly. So you make it off and you see now that what is going to happen. And yeah, I really didn't do that exercise because I thought that you people will play and you will see that what is the effect of that. Okay. And even if it is not done immediately, you can go back and you can see that. That is the thing. Okay. But I want that whether you are able to understand the logic behind whatever the sir has taught you. Okay. That is required. Okay. Stable. Okay. Case 3? Yes. Fine. They did. Case 3 already they did. So, yeah. Then you do the other two, 4 and 5, the last two. And I'm telling you why this problem is required to be understood by the dimension wise, because you will find that same problem you have to solve with different dimension in the next problem. So that's why you see that what are the things are required, what is the dimension you are using, just little bit of that idea you create. It will be helpful for doing the next programming.
think you need to understand, yeah. And it also helps you with math. Even if you don't know some commands, you can go back and, yeah. It's different between each person has different style. Unless you run it, you probably don't understand the theory. You know, you always can go back and see what's happening.
And once the program is running, then what you will do, you will play with the parameters. Okay, then you will see that learning rate, if you change, what is the effect of that? Then QR, what is the effect of the weighting matrices? So these are the parameters you will change, and you will see what is the effect of upper bound of the delay. So these are the things you do and check that what is the effect in the system response. So I suggest you that you take a cup of tea, and because already 3 o'clock, and with that you continue. Okay. Hello. Okay, so I guess that how many number of cases you have reached? Up to case 4. So last one is the final one, that where you have to know that how the Q learning is working. But I need to know that whether the initial parameters and where the random delays and packet losses are defined. Have you understood that how it has been done? This part basically. Little bit here also you spend time such that you can understand that how the delay and packet losses are generated for this particular system.
So, can you just line 50, 51, those initialization of the user into matrix? I mean, from line 50.
So that is required to calculate that the B matrix, BZK.
And the math equations are in the slide. I think that's what he said earlier.
Here you see how we are calculating. Some slide I showed you now that here.
Keep going back. Okay, one more. Yeah, that's
Yeah, this is the formula.
the lecture one. But it's there in other slides also.
Yeah.
Lecture one is basically gives you the
Can you sir just scroll up?
Acha, okay. Shall I maximize?
No, sir, just scroll up the 18. In the IS now.
Okay, so for practice means now you need to do, because you see rest, if one program is clear to you, you will find the rest of the program is not that much, will be tough to understand, because I saw that it is similar way it has been solved. Okay, so whether your concept is clear or not, it will be understood if you now start to solve the problem 2. Problem 2 basically what we want, that same problem like problem 1. Here you will find that the continuous time batch reactor, here what is the dimension of A matrix? 4 cross 4. And what is the dimension of B matrix? So it is a basically MIMO system. Okay. So now the same thing means is this modular way what you have done to solve this batch reactor. I want that you should solve the same thing for the inverted pendulum also. Same way. You will proceed same way the inverted pendulum problem. Once again I am showing you. But now the thing is that the dimensions are different from the previous one. Here A matrix dimension is 4 by 4, but now you see the B matrix is, it is a scalar input we have now. Okay. So with this now exactly the same way what you have developed the modular programming for the batch reactor, case 1, case 2, case 3, case 4, case 5, exactly the similar way you will solve this one also. Then what will happen, that whether your dimension of vectors, what it is defined inside the program, it is clear or not, then it will be clear. Okay, so please you do it once you will complete the case 5. For the same thing you can copy, but you have to be clear that dimensions and the values you have defined correctly or not. And when you will do the Q learning, at that time you can use these parameters, that initial stabilizing policy, these are the matrices, or these are the values you can use, but regression function is same like earlier one what we have taken. Okay, and you can add the noise with a 0 mean and variance is 0.06. Okay, so this is the additional information it has been provided for the inverted pendulum, and you now try to do at least few cases you try. At least I am not expecting that you will do all the cases, but at least 2-3 cases you will try for this particular problem also.
So
It should go up. But I think you need to take pieces out and that's what how you're planning it. You need to take pieces and then just like what's the same, you make it 50 pieces, pull out the code and make it a suspense line. If you run it, it will work. You can want to break it down. Case one, stand alone.
anyone tried that 2, problem 2? No? You're trying. At least case 1 you do for the problem 2. Case 1 is very simple. That's why I'm asking that can you do for this the case 1 at least? Done.
Starting part of the code. Problem 1.
Problem?
How delay and bulk
Delay is not required. Case 1, why delay is required? Just you discretize it.
No sir, problem 1.
Oh, problem 1. How the delay is defined.
The starting code at IND and underscore what are those?
Okay, here.
Yes sir. Define the random delays, the first two lines, IND and underscore.
Basically, what I understood that they are actually having some bound of the delay. That's why here they are calculating that you see if you follow first they are defining the iteration, okay, and then after the iteration they are defining the ND, that is ITR by IND. That is that you proceed because I think that with the number of iteration it is important to have that relation. Exactly, I am not knowing that what is the relation, but we need to explore that one because that's why I am telling. Just you plug in and you see that ultimately at least for one step what is the value you are getting. Then only the things will be clear. What I am saying, you understood na, that just take pen and take the values and you calculate at least one step. You will find that the relation, it will be clear.
We have increased INT from 50 to 100.
Okay.
The converting time is increased.
Okay.
What is the relation? What does it
Signifies. Okay. Okay, I will look into it. That what.
And then the next one, and understood why you are dividing iteration by ND. Two lines only.
Okay, fine.
Also, I show case 2, E is within the sample. So then I don't need that assumption of this So those are things you will rise into the end. But that's what I didn't bring that copy, I didn't bring that, but I thought maybe I should
Okay. You are getting the gain. Gain also?
Previously, gain was 2 cross 4. Here I have omitted that. The original K1 I'm getting. K1 I have the G vector, so 4 cross 1.
Gain also the dimension accordingly it will be, yes. Because only one input you have.
Minus K into X I have.
Yes, yes. You have that. Means it will be only a row vector. না এটা হচ্ছে অ্যাডমিসেবল কন্ট্রোল, মানে এটা এখন লাগবে না, ঠিক আছে, সেটা দিয়ে দিস ইজ দ্য অ্যাডমিসেবল কন্ট্রোল ফর কিউ লার্নিং ইট উইল বি ডিফাইন, হ্যাঁ initial control what you have to define that is given this. So if you see the schedule, tomorrow second half there is no lecture, okay? Only the first half we have lecture. Have you seen the schedule? Okay. So can you tell that why we have not continued the lecture? Why suddenly second half is? Yes. So the second half has been given. You see all the problems we are not able to solve, and definitely whatever the question you raised, I will address you in either in WhatsApp. I will post that. Okay. If I am able to, I have to think that one. Little bit I have to do that what exactly they wanted to say. And in the meantime, you will find that you will do this in the second half, tomorrow second half in your own place. You will try other programs, okay, and you will write what are the queries you have, and again maybe in the next tutorial session, some of the queries we will address first, then we will go for the new set of problems, okay. With that, we are concluding today, and have a good day, okay. Thank you.